Hey everybody, this video is going to be about the dot product. So far we've talked about two operations really, vector addition and scalar multiplication. We want to add to that the dot product. So the dot product, sometimes also called the scalar product, because if you take the dot product between two vectors, you get just a number of scalar. So how does the dot product work? What is it? Well, geometrically, you can think of it, it has to do with the projection of one vector onto another. So if we look at that orthogonal, the perpendicular projection of, say, in this case, vector v onto vector u, so we're looking at sort of what part of v goes in the same direction as u. The dot product ends up being the product of the magnitudes of u and that part of v that goes in the same direction as u. So that's what the dot product is. So then what happens in this case, where I've got two vectors that are perpendicular? What happens if I took the dot product of this vector v with this vector u? Well, since there isn't any part of v that's in the same direction as u, the magnitude of that would be 0, and so this dot product would be 0. How about in this case? Well, with the part of v that's in the same direction as u, sort of along that line that u lies on, being in the other direction, in this case what we're actually going to get is a negative value for the dot product. And so to firm this up a bit, we can look at one way to compute the dot product. You'll actually be proving this as part of problem set number 2. We can find the dot product of two vectors by multiplying the components of those two vectors by each other and then by the cosine of the angle in between them. So hopefully geometrically you can kind of mesh this with what I said about the dot product being the product of the magnitude of, say, u and the part of v that's in the same direction as u. And then it actually turns out that if we want to compute dot products, it's sometimes easier than that if we know the components of vectors. So if we've got two two-dimensional vectors, u and v, then the dot product turns out to just be the product of their first components added to the product of their second components. So in the case where we had maybe I hat and j hat as our basis, then we take the x components of u and v, multiply those together, we take the y components of u and v, multiply those together, and then the dot product is the sum there of those two pairwise products of components. And that extends nicely into higher dimensions, the exact same thing. To find the dot product to higher dimensional vectors, we just pick off the components and multiply them by the components of the other vector, and then add all those products up. And so it's not immediately obvious, at least to me anyway, that sort of that pairwise product of components added up is going to be necessarily the same thing as the more geometric interpretation that we talked about at the beginning. So we'll explore some of that connection as we go on. So think about that some. And also, we know how to compute the dot product in a couple of different ways maybe. What kind of properties could we expect out of the dot product? Is it going to be commutative? How does it handle scalar multiplication? How does it interface with vector addition? What happens if you take a vector and take the dot product with itself? So think about some of these things. I'm not going to answer them now, but see what you can come up with, and we'll talk about it in class. You guys have a good day.